Good morning, good morning. So, let me share. Good morning. We basically discussed in the last session that how we can write the program for DCOPF. Good morning. Uh, and we were using, quad prog function. So in quad prog, we have to basically define certain parameters. So I think if we were here. Okay, so for quad probe, we have to define H and F. So far we were able to define HF and A and B. Okay, so this was already discussed. Now let's see the equality constants, A eq and B eq. What are the different equality constants? So if I go in the OPF formula, the OPF formulation, it is basically available. We were in H and F, so objective function was already handled. Then this constant was basically already considered in AX. Then constant. So one is this, and one is so these are equity constants. Let's try to solve it. AEQ X equals to BEQ. So I can see that the last equation is only single equation, so that is fine. We have n number of these equations, basically the power balance equation. So these are basically n in the number. So I will, so I have defined these. Then I will define n number of equations. So I will define EQ first of all. So it is basically like all are zeros and the dimension will be a number of nodes. So we have defined number of nodes as a n and then number of variables. So variables we have defined all the thetas and p's. So thetas are equals to number of node plus number of generators. So this will be the AEQ, and then BEQ is basically let's say zeros only. So just assignment, and that will be n by 1. Okay, so this will be AEQ. Now, to define for each node, we have to write down these equations. So I can apply a for loop I equals to 1 to n. Okay, so this is our for loop. I hope it's visible, right? So we can write it like this. Then let's see how we can define it. So if I go below here, you can see that I have to put all the x related terms on the one side and like the terms which are constant on the other side. So we had a equation like PGI minus PDI equals to summation over j 1 to n, and it was I think delta I minus delta j upon xij, and this was for all the nodes we were supposed to write down. So if I put everything on the one side and let's assume certain node is there. So what I will do is like I will convert PG1 on the one side. So it is PGI, then minus of summation delta I minus delta j upon xij equals to PDI. So this is what I can place that. Okay, these are my equations, and for this 6 bus system of the wooden Woolenberg, we can see, let's say, so the data is available here. So I can see like on bus 1 there are 2, 4 and 5 3 connections. So I will just draw it for bus 1. So it is basically generator, certain load, and then three connections are there. So which is one is going to the 2, one is going to the 4, and another going is to the 5, and this is bus number 1. So I can say it is like PG1 or P1 minus if I put the J for rest of the other nodes, the Xij will be infinity, and that will make this entire second term, which is like power Pij equals to 0. So I will only have these even if I put this summation, I will have only for 3 lines. So that will be delta 1 minus delta 2 upon x12 minus then delta 1 minus delta 4 upon x12 minus delta 1 minus delta 5 upon x1. Sorry, I made a mistake. This should be x4 and this should be x5 equals to PD1. So this is the equation, and now let's convert this equation into A equality. So we will have some A, then some X. So X is already defined by us. It is first of all angles. So delta 2, delta 3, delta 4, delta 5, and delta 6, P1, P2, and P3, and then it is equals to the demand. So we know that this will be like uh, PD1, PD2, and up to PD6. So this will have a n by n plus ng dimension, and this is n plus ng dimension, and this is n by 1 dimension, ng by 1. So these are the dimension of these matrices. So this initialization we have already done. So what we have to do is identify the delta 1. What will be the delta 1? So I can say it is minus of 1 upon x12 minus of 1 upon x14 and minus of 1 upon x15. So this is the first term with respect to delta 1. Then some delta 2, delta 3, delta 4, delta 5, delta 6, P1, P2, and P3. So these are the respective columns of this AEQ. So this is our AEQ matrix. So delta 2 is basically 1 upon x12, I think. It's clear. Then delta 3 is 0. It is not present. 1 upon x14, 1 upon x15. Delta 6 is 0, and P1 is plus 1. P2 is not there. P3 is not there. So this is what a equation will look like. Now let's try to fill those part here in our formulation. So for first bus, I have to first of all identify what are the different nodes it is being basically connected. So I have to first of all find out where is the one available, like what are the different connections to the node 1. So I can apply certain uh, from position. Okay, so from positions are equals to, let's say, find. So I will try to find one in the first column and then one in the second column as well. So if I try to find one in the first column, it is dot branch all rows comma 1 equals to I, whatever is my node. So this will give me the if ith node is at the from position, let's say 2 position. If ith node is at 2 position, I will use the same condition and see, look at the second position. Okay, so I'm not certain but what will be the outcome of these. So what I will do is I will first check whether it is giving me what I want. So okay, first of all we have to load the case. So let's say uh, load case dt equals to load case, and I will put the case 6 ww here. So this has been loaded. Now let's see, calculate this one. So instead of I will place 1. uh, let's see what I get. So F position is 1, 2, 3, and T position is empty. So that is perfectly fine, because this is what we can see, that first generator is at 1, 2, and third position in the branch. Now let's see what is there with 2. If I use the same code, and I will place 2 here, I will place 2 here and enter. So it is 4, 5, 6, 7, and 1. So F position is 4, 5, 6, 7, and T position is on the first row. So if we look at the data, so it is 4, 5, 6, 7, and second position. So these are the different lines which are basically connected to the different like ith node, if I say. So this has, once this has been identified, uh, I can apply a loop. Okay, so that loop will be basically, I have to put everything here. So let's say for j equals to 1 to length of f position. So let's say whatever is the length of f position, I will apply that loop for this particular one, and I will place, like, whatever is the impedance with a negative sign at ith column and ith row, and rest of the others will be positive. So I will simply put aeq I comma I equals to aeq I comma I plus 1 divided by dt dot branch, and okay. So now we have to identify which branch actually we are talking about. So it is in the available in position, and jth number term will give me the branch position, and where is the x value? So it is 1, 2, 3, 4. Fourth column is basically x for that. So I will put 4 here. Okay, and let's uh, agree to this particular part. So that will be done for, like, first part. Then I will put the same thing with the positive sign. So this should be with the negative sign. So I will put a negative sign here, minus, and then the same thing should be placed at I comma jth location. So I comma and jth location is basically the node number, not the current j. So the node number will be like, f position, or okay, wait, this will be available from the row number, and whatever is in our dt dot branch. So we have dt dot branch, and we will put position here, f position, and j. So this will give me the branch number, and in branch number, if I'm looking at the f position, I will place the second part here. Okay, so let's see, just to initially, what I will do is, instead of using this, I will put a temporary variable, and just for the correction point of view, like whether we are doing it right or wrong. Okay, so this is it. Then I will apply the same loop for t position as well. Control c, let's say, and enter. Control f, and instead of f position, it will be t position, and the branch will be basically whatever is the t position branch, then t position. And if we are looking at the t position, so if, let's say, the ith node is on the from node, then we have to place the second, or instead of the, the another node will be at the first position. So this is like, we are doing it. So let's put a counter here and try to solve it. Okay, so add to path. So far so good, everything is good. So we have developed a, we have developed a b, and let's step So for first node, I have obtained F position is 1, 2, 3 and T position as an empty matrix. So for first node, it is quite obvious that 1, 2 and 3 are the number of rows in which the first branch is basically connected. So we have identified the connections. Now, if I go, it is like, value of J will be 1 and then AEQ should become some negative value. So minus 5. So just note down then that it is 0.2. So that will be basically 5 value. Okay, so let me do like this. So this is X values, right? And these are the different X values. Okay. If you have any doubts, like why somebody can suggest me some other alternate approach as well, because its programming is basically you can adopt a lot of different thoughts or logic to obtain the same outcome. So yes, there are multiple ways of doing it. We were just like doing it instantly. So that will be point two. Then if I further run it, this zero point 0.5 will go and positive, and this is like branch number 1 2. So at the second position of the AEQ should go with the positive sign. So let me see. So it has not been updated. So I think it is temporary 2. So it is I1 comma 2 should get certain value, but it is not okay. I'm adding that to, okay, so this is the genuine mistakes which we are making. So what we did is like we created a 1 comma 1 element, and I just initially subtracted as that 5 value, and then I added that 5 value. So this is coming equals to the same value. So instead of this, I have to place this part. So this is how we should do debugging all the time. Okay, and again I will see whether my matrices are basically what I want them to be. So let's see if I'm doing it fine. So yes, you can see here, uh, like very first term is minus 5 and the second term is 5. So we are basically able to obtain these values. If you see, so we were able to obtain, let me change the color of the pen and draw color. So we have placed this one and this one so far. Okay, now then step in, it will go for the second part, and the second part it will update the first value. So instead of minus 5, now it has become plus minus 10, and then the fourth element should get certain value. So you can see like yes, minus 10 5 0, and the fourth column is also like added that particular value. So I can say here that we were able to place this part and up to this part now. So this has also been, so this and this part has been placed. And, if I look at the third position, okay, so step in and check. So it is 3.33 because I think the reactance is zero point 0.3. So that is 3.33 has been added to the AEQ, and it is quite visible here. Okay, so minus 13.33, 5, 5 and 3.33. So we were able to, place this as well as this part. Now, one thing is we have to place one as well. So that we can do at the end. So let's say it will not run. So stop quit debugging, and let me place. Once I have done it, I will place AEQ comma, and we are placing for the generator. So we have to identify um, whether ith node is a generator bus or not, first of all. So I have to identify like generator position. Okay, so generator position will be basically I will again use the find command, and I will look at the dt dot branch, not branch basically, in this time I think generator, and I will look for the first column and equals to I. If it is equals to I, then I will get certain value in the generator position. Okay, so if you see here uh, in the generator data, 1, 2, 3 are basically our different branches. So let's see. We will get certain value, and then I can place, if there are multiple generators, we can apply another loop. Let's say, so I k equals to 1 to uh, length of g position. Okay, and this loop, and then I will place a eq I comma and the position number, right? So it will be basically and the same thing for first, n number of places are for the angles, so I will place n plus the g position. Okay, and I have to look at the place, so this is g position at kth part. Okay, so this is what we will place, and this should be equals to 1 only. Okay, so we are going to place 1. So if you look at here, like we just simply have to place 1. So we have done this part. Now let's talk about beq as well. So at the end I can say beq I comma 1 will be equals to dt dot bus, and whatever is the I comma, and the demand is available in the bus data and at 1 to 3rd position. So I will place 3rd position here. So this is at 3rd position. Okay, so this is how we can basically uh, place the a and b eq. Now let's see whether we are able to build it or not. Just to see whether this is working fine, I am just making this 1 equals to 4 for the time being, and then I'm trying to solve it. So I will run again and check whether the 4 has been appeared in the data or not. So if I see the generator data, let's see. So the very first bus is 4th bus. Okay, so now if I step in and check for aeq, then this part I think we were already placing them here. Continue, and aeq was the same which we have understood earlier. Now it should, so there is no generator now at bus number 1, and we have placed them at a bus number 2. So step in, and it will not run for that. And beq, so in beq it will be 0 because there is no load at the bus number as well. So you can see the 3rd column, it's 0 4 1 2 3. Then step second time, so f positions are 2 4 5 6 7, and t positions are 1. So there are 5 basically branches. So one is 1 by x12. Then for this second node it will be basically minus 1 upon x12 minus 1 upon 4 5 6 7. I think these are the branches. Let me see. So the branches are basically uh, 2 is connected with 3 4 5 6, 2 3 4 5 6. Okay, so x3 4 5 and 2 6, so with a negative sign each. So this is delta 2. So some delta 3 will also come, and that will be 1 upon x23. Delta 4 will also come, x upon 2 4, and delta 5 is also there, x25. Delta 6 is also there, so x26, then 0, and we have a generator here, and we do not have generator at this particular part. So this is what we need to see. So let's see whether we are able to make the conditions like this. So step in, and it will place the second element. Okay, so a negative part in the second element and then positive in the first element. So this has been placed, but not the other way around. Okay, it is actually from the four from positions first of all. So it is basically looking at the like whenever 2 is at the first place, so that is fine. Then it will solve and then give me the again the x 2 4. Okay, then it will go and continue solving the like 2 4 2 5 and so on, so up to like the delta 6 it has been placed. Now from the t position it should replace the first part, so it has been now there is an issue here. Okay, yes, what is the issue? I'm able to identify it. The same issue which we made earlier, it should be placed with this term. Okay, control V and quit debugging, run and continue, then run and see whether we are able to find it. So first part and then second part is, yes, you can see here the second 2 comma 1 element is also placed with a particular value, which is again 1 upon 0.2, which is 5. Okay, so then if it is generator, so let's see. So generator, yes, it is generator and available at the second position. So I will put it like this and I will place a generator at the second position. So you can see at the last second last in the second row is being placed with a 1. Okay, then BEQ it should again come 0. Okay, so BEQ will be 0 again. Okay, because there is no load. Then if I look at the third generator and so third bus, so third bus is connected with the 2 and 5 6, 2 and 5 6. So it is not connected with the 1, so I will place 0. Then it is connected with the delta 2, so I will place 1 upon x 2 3, then minus 1 upon x 2 3 minus 1 upon see again. So 3 is connected with the 2 and then 5 and 6. So x 3 5 and minus upon x 3 6. Then there is no connection with the 4, so you can see like 4 is basically 0. 5 is available, so it will be 1 upon x 3 5, and 6 is basically available, which is 1 upon x 3 6, and this is also generator, so 0 0 and 1 will be placed. So let's see we are able to obtain these values or not. So I will continue to the next part and then check AEQ. So if you look at the third number row, uh, these entries like with the second 3 is connected with the second node, then fifth and sixth, so that those has been placed. Okay, now just quickly look at the fourth node, which is as a generator, but we have okay, some error is there. Let me see why it is happening. So continue, 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 and I value is 3, and then once I value is 4, some issue is there. So let's see. So some AEQ has been basically putting up for the fourth position as well. Now then T position for the 4 is basically yes, one part it is 1 and 2. So let's see the T positions are second and fifth column. So I'm able to solve it. I'm able to solve. Okay, some issue is coming here, and that issue is it should be replaced with the T position. Okay, so let's again see, and let me remove this, and this is for I equals to 1. then I equals to 2, 4, 5, yes, and continue. Now let's see what AAQ has been there. So we were able to build this AAQ. You can see it is perfectly symmetric, and there is second generator at the second node, there is a third generator at third node, and the first generator is at fourth number bus. So we have basically placed those generators perfectly, and you can see, like, some AEQ matrix has been built exactly what we have, and BEQ is also like 00 and 70 has been built. Any doubts in this particular part, like how we are like writing these codes? If you have any doubts, you can ask them. So now I will again, so this logic has been explained. Like if it is 4, it will be 1. If I keep it 1 and then solve it, you can see that the first column will basically AEQ will be changed, and this part will become 1, the 1 by 7 part. Okay, so we have obtained AEQ and BEQ. Now, what else is needed? One delta equality was also there. So we have to identify that which bus is reference bus. Okay, and respective angle will be made equals to 0. So if you see in this particular data, I have explained you that go through the case format file, and this 3 represents the uh, reference bus. So wherever is this 3 available, that will give me the reference bus data. So I can, like, just to write the generalized code, I will keep, like, condition a reference bus number is equals to find the 3 in dt dot bus information, and I think all the rows second column. So whatever is the second column, uh, if it is equals to 3, it will give me the bus number data, and respective entry in AEQ will become 1. Okay, so AEQ, I have to add another row because those n number of rows in AEQ represents for power balance equation. So we have to go for n plus 1. So I'm just, using and plus 1 because and is like whatever is and extra row, and the column will be the reference bus number. So I will get that number and I will put it here. So it is in dt dot bus, then reference bus number comma 1. So this should be placed equals to 1. Okay, and then same I have to do that BEQ and plus 1 comma 1 should be made equals to 0, that this angle should be equals to 0. Okay, so I think if I solve it, you can easily see that delta 1 is equals to 0 has been placed. And if I change the reference bus, let's say, let's change the reference bus. Instead of this 3, if I make it 2 and make it 3, the delta 2 should be basically changed. So let's again run it and check whether we are able to obtain this one. So yes, delta 2 has been placed 1 and equals to 0. Okay, so this is how we can basically try to build our own program. And now let me change it again just to keep the same example. So we were able to build, like from the formulation, if I look at, we were able to build AEQ and BEQ as well. Okay, so these has been built. Now lower bound or upper bounds. So those are very easy. What I can do is basically go here, and I have defined some X. So this was X defined, right? So I will copy this one. Okay, and I can paste. Generally I build here. So X has been defined like this. So I will build, like, some lower bound. Lower bound is B. Okay, I will build some X note and I will build upper bound. or I can keep upper bound above and lower bound below. So it is equals to certain values. So I'm not going what are these values first of all. So some theta values are there. So thetas are, we know that it should be equals to either pi or pi by 2. So I will use 3.14 as a pi multiplied once, and then number of angles will be there. So n comma 1. So then power generation. So let's make it either row vector or column vector. So let's make it column vector, comma n. Then power generation. So it is maximum is available in, like, this gen data, and 1 2 3 4 5 6 7 8 ninth position is p max. So I can place, like, dt dot gen, and then all rows comma ninth position will be the this information. The same I can use the same information, control c here, and instead of, like, pi, the lower bound will be 4 angle minus pi, and then the minimum is available at 10th position, so I will place it 10. Now, if let's say sometimes we also provide some initial value x naught, so angles will be at 0. We know that angle should be at 0 position initially, and power generation should also be 0. So I will put zeros, and I will use basically n plus ng comma 1. So yes, simply, like, I don't even need these brackets. So this is my x naught. Okay, so all the 9 values, and let's see if some mistake I have made here as well. So 1 comma n comma all rows comma 1. What is the error? So word cat always being connected, not constant, line number 16. So let's see what is line number 16. 1 comma n. Okay, it should be n comma 1. N comma 1, and let's see. Now it's fine. So you can see like the pi and 200 150 180s are basically values. So once we have built everything, I will call my function quad proc. Okay, so I don't want to type everything, so what I will do is open the help file and copy it from there. So let's copy from here to here and place it in our program. Shift home, control X and control V. Okay, and then remove this particular part, and let's hope that it works. Yes, I think it has solved. So problem is infeasible. Now can you tell me why this is happening? Anybody? Exit flag is -2 and the problem is infeasible. Can anybody tell me why this is happening? Let me show you the code again. So these are basically, like AEQ and BEQ. This is my BEQ, like, the demand at first, second, and third is 0, and then 70 megawatt, 70 megawatt, and 70 megawatt. And if I show you the other variables, which is like, input A. So this is A. So it is simply like, linearly, like what are the different branches available. If I show you the B, like what are the different line flows. So line flows are given, like, multiplied with the reactance. So it is like P max, which is in megawatts, multiplied with the whatever reactance. So these information is available here. So some issues here, and I have mentioned it earlier, that there is some issue in this particular equation BEQ. Anyone who can answer it, like why the solution was infeasible? Ankit, anyone else who wants to answer? You can put like like if you don't know, you can put we don't know. At least I will know that you are listening. Okay. So yes, obviously you don't must have slipped it because I said it once. So there is a, is it singular matrix? No, I don't think so. That is the issue. I mentioned you when we were discussing ECOPF and DCOPF that okay, what is the maximum value this angle can have? It's a pi 3.14. What is the maximum value this angle can have or minimum value it can have? It's a minus 3.14. So the above difference can be twice of 3.14. So if I calculate, it is 2 into 3.14 is 6.28. And the xij was how much divided by xij? It was, I think, 0.2. So divided by 0.2. So it comes 31.4. So this power flow can have a maximum value of 31.4. Okay. So I told you that everything, all of these values should be in the same format or same unit should be there. So let's say if I open case format and what are the different values we basically used. So yes, in the bus matrix, we used bus number, we used a reference bus number, like whether it is slack bus or not. Then the demand is given in megawatt. That is point number one. Apart from that, I think we did not use anything from this particular uh, like metrics. Then generated data, if you see, we used the very first column that at which and bus number the generators are there. Then reactive power we did not use. We used ninth and 10th part. So ninth and 10th is basically the maximum and minimum generation, which is also available in megawatts. Then we did not use any of these information. In branch data, we used the first column, second column. So first column is from bus number, second column is two bus number. So we used it to identify. Then is basically reactance and it is in per unit. So your units are not matching. So we have to convert everything in per unit first of all. What I will do is as soon as I load this particular case, I should convert all of these values in per unit. So let's say dt dot bus, all rows comma 3 and 4 represents p plus jq. So let's convert q also in the per unit. So that should be basically equals to the your demand should be equals to should be converted into per unit. So let's say dot divided by dt dot base mva, and this is defined as a base mva 100. Okay, so it is already defined here. So I will put it like this, and let me see if some no. So basically, the bus is instead of 70 megawatt, it is 0.7. Now, same thing we have to do for the if you simply look at the formulation, uh, demands has been converted into the per unit. Then PG is variable, so no need to convert into a variable, but power flow and generation are also available in basically megawatts. Let me see, power flow is also in megawatt or per unit. So these are also like MV ratings of the. So MV ratings are given. So this should also be in the per unit. So I will put dot branch all rows comma and 6 to 8. 6 to 8 uh, should be equals to this value dot divided by dt dot base MVA. Okay, so we have converted that into base. Then dt dot generation data. Okay, so generation limits basically has to be converted into this thing. So those informations are available at certain locations. So let's say look back the generation data, and the generation data is 4 5 is qmax qmin. So I'm doing it, like when we are going to solve ACOPF as well, we have to convert q as well in the per unit. So 4 5 and 9 10. So I will put here like 4 comma 5 comma 9 comma 10, and these information should be converted into per unit. So let's say all of these divided by dt dot base MVA, and let me stop it, run it again. Let's hope no error is there, or we are able to solve it. So now the output, you can see the exit flag is 1. We are getting some x value, so certain angles are given. Okay, and certain powers are given, like 0.5 is basically per unit power, so it is 50, and 115 and 45 megawatts. So these are the solution. Now if I look at the lambda for this particular part, let me just look at the equality constant. So it is coming out minus 10. So basically, sometimes as the nature of the quad probe formulation or lane probe formulation, if we have written it, this AQ are like the equality constant which provides me the lambda, uh, where PD was on this side, and this all the X were on this side. So to get a positive lambda, basically the actual lambda, I have to multiply everything with a minus sign. Okay, that my PG should be usually, like, if we write down the lambda equation, we economic load dispatch, we have written always, like, plus the penalty term lambda multiplied with PD minus PG. So PG was with the negative sign and PD was with a positive sign, and then we basically put these constants here. So this PG should be negative. So what I will do is I will put once I have done it, in this particular code, AEQ and BEQ should be placed with a negative sign before the reference bus. Reference bus cannot be like with a negative sign. So what I will do is I will put AEQ equals to minus of AEQ, and BEQ equals to minus of BEQ. I don't know whether this is how I can put or not, but let's see. If some error will be there, we will see. And then if I look at the lambda, they are coming positive. Okay. So now the question is, how do we know that whatever we have written is perfect or not? That is a very important question. That how we will be sure that whatever we have obtained here is like the true values. So for that, I asked you to like install this mat power. Okay, and once the mat power is here, I can, there are direct solutions or direct commands for these existing cases, where you can easily solve these OPF and DC OPF and power flow. You can make bypass. So there are a lot of commands here. So in documentation, if you see, I will simply put DC OPF and K6WW, and it will give me the answer. Okay. So the mat power. So this command is from the mat power. And if I look at here, you can see the results are different. Results are very much different. Now, why this is happening? So it is 50 is fine, then it is coming out 88 and 71. So let's see where is some mistake. So we have to debug that mistake. And the lambdas which we have solved was 10 point something, it is coming out equals to 11 point something. Then angles, if I talk, so voltage magnitudes were, we have assumed 1. So angles are available in degree, and whatever like we obtained is in radian though, but we have to check what is the issue here. So who can like tell me what issue is there, and who can debug this particular code and solve it, and like verify this met power results. One more thing is like here as well, like if you see, these are the power flows. Okay, and let me see if we have violated any of the power flow. So the branch data is this, and these are basically 40, 60, 90, 80, 20 is 4, 5, and none of these has been violated because none of these has been placed to the fixed value. So we can see that line limits are not uh, like enforced, but power outputs are something else. Some issue is there. So, and that is only because of the cost functions, I think. So cost functions will affect it, and what we made, I think, in H and F, that is the issue. So what it can be. Okay. So what was the cost function? I don't think so. You will be able to find it out. So the cost was for any generator is A pi square plus BP plus C. Okay, and this is basically in dollars, and here P is in megawatts. So what is the unit of A? Can somebody tell me? If the cost is obviously in dollars and P is in megawatts, then what will be the unit of A? Should be dollar per megawatt square. B will be dollar per megawatt, and C will be in dollars. Now, if I have converted this into per unit, so instead of this P, I am basically writing down cost function is like, the A is same, and that is dollar per megawatt. And I'm multiplying it with the per unit cost. So these variables has been now changed to per unit. So if this has been per unit, I cannot multiply them. So this variables has to be converted into the uh, megawatts. So how can I convert, I think, Roshan? Per unit to megawatt, how can we convert? Multiply with the base value. So these are in per unit. So plus B, and this PI is also like, per unit plus C. So this entire notation is wrong. So we have to convert this PI, which is in per unit, into base value, and then square plus B and this PI per unit into base MVA. Okay, so this is what I issue here. So if you can see, we simply used twice of this function. So instead of twice of this function, if I solve this particular, okay, wait, part, I can say it is A into base MVA square into PI per unit square plus B into base MVA into PI. So this B coefficient should be replaced with this particular part, and A coefficient should be replaced with this particular part. So what I will do is I will multiply this here with the square of dt dot base MVA multiply dt dot base MVA in the A part, and function was basically zeros, and then dt was this, so it should be multiplied with dt dot base MVA and multiply with this particular. So the cost coefficients should be like this. Now let's see whether we are getting the same solution or not. Okay, so if I solve it, I obtained certain solution, and if you see the x, it is same 50, 88.07 and 71.93. So 50 is okay, and that is the limit. Then 88.07 and 71.93, and so let me like, okay, it will not clear that one. Let me see the lambda as well. So it is lambda dot eq lim. Okay, so these are the lambdas. Now these lambdas are for per unit quantity, so we have to convert them into the megawatts. So these lambdas basically these prices are basically dollars per unit. So I have to convert this answer by multiplying this MVA is 100, okay, and by dividing it by 100. So we have earlier multiplied it. So these are the different lambdas. Now again run DCOPF for this case 6WW and see if we are getting the same solution or not. So if you look at the power generations is 50, 88.07 and 71.93, and same we are obtaining here. It is 50, 88.07 and 71.93. It is in per unit, so we can multiply it with the 100. Okay, base. So these powers are perfectly fine. If you look at the lambdas, it is coming out 11.8989, and here as well you can see it is 11.8989. So like approximated to the 9. Okay, so we are getting the same solution. Angles, if I look at, it is 0, negative 2.99, and if here if I see, the angles are 0, negative 0.052, but this are in radian and those values are in degree. So I request you to convert those values in degree and check whether we are getting the angles as well, right? So we have checked that p variables are exactly same, angles are also exactly same, and then lambdas are also exactly same. Then you can calculate the power flows as well. Like all this information is available to you, then you can calculate the power flow. So do you have any doubts so far? You can ask it, and we are going to write multiple codes with different methods, and for verification we can use the existing programs. And the exercise here, like for this programming hands-on, is not to write DCOPF program. That is not at all the exercise, because DCOPF you can directly use the inbuilt program in the Met Power. Okay, once you install it, you can use it. The exercise is obviously while you are like doing some research or solving some other problems, you will not have inbuilt programs for that. And to solve any optimization problem, you should know how I can model my entire like mathematical problem. So which we have like understood here that this is how we can uh, write the entire mathematical problem. And once it has been written, how we can convert this entire mathematical problem into the MATLAB inbuilt functions. So in MATLAB, we have linpro, quadprog, fminco. So that is what basically the learning is behind. And so this is it from my side today. And if you have any doubts, you can ask me. We will have another session at 2 to 4. Okay, and tomorrow it will be just let me remind you, it is Saturday, so there will be 5 hours. It is 10 to 1, and maybe 2 to 4 are like if I'm there may be like I will not be available at 2, so we will shift it to 3 to 5. Okay, so 10 to 1 and 3 to 5 will be our class on the Saturday. So I think that's it. Thank you everyone. Let me see.